Hi everyone, good morning. So this year this is our first morning class. Okay, so in these morning classes we will study the remaining graph theory. Okay, and we have no rush, so basically we don't have to hurry. So basically what we will do, in every lecture we will study only one or two topics. Okay, so small lectures we will have, or maybe 1 hour, 1.5 hour. Okay, so this is what we will do. And in the evening classes the digital logic is going on. The first class of digital logic was basically just an introduction. Okay, the digital logic, the actual digital logic, okay, that matters in the gate exam, that will start from today. Okay, in the evening class. So the actual digital logic is going to start today. The first class of digital logic, that was just a introduction to what is digital logic, what we need to study, what we don't need to study. Okay, so like that. Now let's study this lecture 9. So in this lecture our main topic is clique, and so this clique number and independent set, this is our concept for today. Now remember, in the last class we have already seen trees and rooted trees. These two concepts we have already seen. You know the difference between tree and rooted tree. What is that? In a tree you don't have root. In a tree, this rooted tree, this is a directed graph. Okay, in this rooted tree there is a root. And one more thing, for example, if you have a tree, like you have a tree, I told you that in a tree we don't have the concept of root. There is no concept of root, there is no concept of child, there is no concept of intermediate vertex. Yes or no? Okay, so basically these concepts we don't have. Intermediate node, so these concepts we don't have in a tree. Now if I give you a tree, for example, maybe a b okay, so maybe this type of tree, you have a b c d e f, okay, g h. So let us assume this is your tree. Now how can I create rooted tree? Like how can I convert this tree to rooted tree? This tree I have, now I want to convert this tree to rooted tree. This is what I want to do. This is what I want to do. I want to convert this. This is a tree. Tell me in this tree, tell me in this tree, what is the intermediate vertex? Tell me, what are the intermediate nodes in this tree? What are the intermediate nodes? There is no intermediate node. In a tree we don't have this concept. In a tree we don't have this concept. So this you already know. What is the difference between tree and rooted tree? This difference I told you. What is a tree and what is a rooted tree? This difference you already know. That tree, this is undirected. This is undirected. Okay, this is a undirected, connected, and acyclic. This is undirected, connected, acyclic graph. And this rooted tree, this is a directed. This is a directed graph. This is a special type of directed graph. This is directed, okay, with root. With there is a root. There is a concept of root. Okay, this is basically directed acyclic graph with, okay, with like I can say one, from root to every node, exactly one path. Okay, with one path. Okay, exactly one path from root to every node. Exactly one path. Okay, exactly one path from root to every node. So this concept we already know. So remember, in this rooted tree we have these concepts. Here in the rooted tree, these concepts we have. For example, what is the height? This concept we have. What is the child? This child concept we have. This sibling concept we have. These concepts we have. This root concept we have. Intermediate node concept we have. Like, okay, what is the intermediate node? What is the intermediate node? Internal node, I can say. Okay, internal node. So what is the concept of internal node? I can say, okay, internal node. So these concepts we have. These concepts we don't have here. Okay, here we don't have these concepts. Okay, so these concepts we don't have. In these trees we don't have the concept of height. There is no concept of height. Okay, this height concept we don't have. This root concept we don't have. There is no concept of root. There is no concept of child. There is no, okay, so these concepts we don't have here. There is no concept of internal node. We don't have these concepts in a tree. Is this clear? Is this clear to everyone? So this we have already seen, the difference between tree and rooted tree. Tree is very simple. Tree is undirected connected graph, undirected connected acyclic graph, and rooted tree is directed. That is a directed acyclic graph, directed acyclic graph with exactly one path from root to every node. So in this rooted tree, we have the concept of root, we have the concept of height, we have the concept of depth, the concept of ancestor, descendants. These concepts we have in rooted tree. These concepts we don't have in tree. Okay, we don't have these concepts in tree. Is this clear? Now, for example, this is your tree. In this tree, we don't have the concept of height. There is no concept of height. We do not define height in a tree, in this tree. So there is no height. There is no ancestor. Like, who is the ancestor of A? Tell me. Can anyone tell me who is the ancestor of A? Can anyone tell me who is the ancestor of A? Like, this concept is not defined. Yes or no? So this concept is not defined. Very simple. Like, who is the descendant of A? Who are the siblings of A? Okay. What is the height of A? What is the height of this tree? What is the depth of A? These concepts are not defined in a tree. Now, I want to convert this tree into rooted tree. Then how to do that? Tell me. Rooted tree with the root. See, this is very easy. If you want to convert this tree into a rooted tree, then this is very easy. For example, rooted tree with the root A, with root A. So what you have to do? Very simple. What you have to do? So you want rooted tree with root A. So this is what you have to make it root. So just make it root. Just make it root. And what you do? The remaining things you just hang them. Okay, you just hang them. Like it's like you pick this, and the remaining thing will hang. The remaining thing will hang. So you can notice the remaining thing will hang like this. Okay, like this. The remaining thing will hang. The remaining things, they will hang like this. Okay, so you can notice the remaining things, they will hang like this. Is this clear? Is this clear how I got it? See, just pick this. Okay, just to pick this. Now the remaining things that they will hang. For example, A is adjacent from A to C. There will be, okay, this A will be connected to C, C will be connected to H, A is connected to B, A is connected to G, A is connected to D, D is connected to E, and D is connected to F. Now tell me, what is the height of this? Like, now I got the height. Okay, so here we don't have height. If I ask you height, then not defined. Then what you will say? You will say not defined. But now here I can ask you the height of this tree. What is the height of this tree? Height of this tree means height of the root. Height of this tree, that means height of the root. Height of the root. So that is basically the longest path. The longest path from root to any leaf, the longest path. So that will be 2. So the height actually will be 2. Okay, so very simple. What is the okay, so this is the height, and this is your root. Now this is your root. And what are children of root? These are the child of root. These are the child of root. Okay, what are the ancestor of E? So these are the ancestor of E. These are the ancestor of E. So very simple. The concept is actually very simple. Now let's see rooted tree with root F. Now what will happen? I want rooted tree with root F. So this is your tree. I want to convert this tree into a rooted tree with root F. Descendant like your, like I can say, ancestor like my father, my grandfather. Those are ancestor. Descendant like my child, my grandchild, like that. Okay, is this clear, Nikhil? So, for example, the descendants of A, all of are the descendants of A. These are the descendants of D. These are this is the descendant of C. Okay. Now, Arpan is saying from A to F, from A to E, there is unique path. From A to E, this is the definition. Exactly one path from root to every node. From root to any node. From root to any node, there is exactly one path. So there is exactly one path from root to E. From root to E, this is the path. From root to f, this is the path. From root to h, this is the path. From root to g, this is the path. So there is unique path from root to any node. From root to any node, there is unique path. You have unique path. Okay. Now let's see rooted tree with root f. Then what I will get if I want to. So basically pick this, and the remaining things will hang. So just make it this, make this root, make this root. Now you can notice. So what will happen? Make this root. So this is connected to D. Now you can notice D is connected to E, D is connected to A, and then A is connected to G, A is connected to B, and A is connected to C, and C is connected to H. So this is what you will get. Yes or no? Is this clear? So tell me, what is the height of this rooted tree? So basically root f. So you are picking this, just pick this, and the remaining things will hang. So you can notice f is connected to D, D is connected to E, D is connected to A, and so on. So what is the height here? What is the height of the tree? That will be height of the root. What is the height of the root? That is from root to the farthest leaf. From root to the farthest leaf. So you can notice this will be the height. This will be the height. Okay, so I can say number of edges 1, 2, 3, 4. Number of edges will be 4. So this is the height of the tree. And what are the descendants of, for example, if I ask you, what are the descendants of D? Here you can see the descendants of D are E, F. These are the descendants of D. Okay, now here what are the descendants of D? These are the descendants of D. Clear? Okay, so these are the descendants. These are the descendants of D. Remember, ancestor means like my father, my grandfather, and so on. Those are ancestors. And descendants means my child, my grandchild, and so on. So these are the descendants. Okay, very simple concept. So remember, these are the descendants of D. Okay. Now, similarly, you can do, for example, if I ask you, what is rooted tree with root? If I want to make the root B, then what it will be? Rooted tree with root B. So very simple, pick this and make it root and make it root. So you can notice B is adjacent to A. Now this thing will happen like this. Okay, so this A, and then this D, and then this E, then this F. Okay, and what will be the height of this tree? Height of this rooted tree. So that will be the length, I can say that height means from root to the farthest leaf. What is the path? So I can say that is basically length of 3. Okay, so number of edges is 3. Very simple. And what are the descendants of A? These are the descendants of A. In this graph, these are the descendants of A. Okay, very simple concept. So this is the concept of rooted tree. You already know. Rooted tree is a directed graph. This is a directed acyclic graph. I told you binary tree is a rooted tree. Yes or no? Binary tree, that is a rooted tree. Okay, and tell me, like if I ask you, okay, anyway, so what is the degree of this? Like what is the degree of this? What is the degree of this node? Degree of this node. I told you degree means number of children. Degree means number of children. So the degree of this node will be 3. Degree means number of children in a rooted tree. In a rooted tree, degree means number of children. For example, here what is the degree of this node? What is the degree? Here, what is the degree? The degree is basically number of children, that is 4. Okay, so these are the simple concepts we have already seen. Now let's come back. So for example, this is your rooted tree, and you can solve these questions. Like what are the children of J? Children of J, these are the children of J, N O P. Okay, because this is your J, so these are the children of J. Next, you can notice ancestor of S. Ancestor of S. This is the vertex. Where is the vertex S? So this is the vertex S. What are the ancestor of S? So you can notice ancestor means father, grandfather, his father, his father, his father. These are the ancestors. MIDBA. MIDBA. Okay, MIDBA. These are the ancestor of S. Very simple. Next, siblings of Q. Siblings of vertex Q. This is your vertex Q. Siblings means, okay, means same parent. Siblings means same parent. So RST. Next, Find the number of leaves. How many leaves you have? So these are leaves, these are leaves. Okay, this is a leaf, this is a leaf, and these are leaves. So these are the leaves. You can calculate. Next, find the least m. Find the least m for which the tree is rooted m tree. So can anyone tell me this? What can I say about this tree? What is the least m such that I can say least m? What is the least m such that I can say it is rooted m tree? Can I say this is binary tree? Binary tree means two tree. Can I say this is binary tree? No, because you can notice this has three children. So what is the least m such that it is rooted m tree? What is the least m? So just find the degree basically. Basically find the degree. So what is the degree? Okay, let's find degree. Degree of every vertex. So what is the degree of this vertex? That is 2. Degree of this vertex 2. Degree of this vertex 2. Degree of this vertex 0. Degree of this vertex 0. Degree of this vertex 2. Degree of this vertex 1. Degree of this vertex 2. Degree of this vertex 1. Degree of this vertex 0. Degree of this vertex, can anyone tell me what is the degree of this vertex j? That is 3. Degree of this vertex 0. Degree of this vertex 4. So actually this is 4 array tree. Yes or no? I can say because this vertex has degree 4, this vertex you can notice this has 4 children. So I can say this is your 4 array tree. This is your 4 array tree because this vertex has 4 children. So the number of children you can notice this has this vertex has degree 4. So this is your 4 array tree because m has 4 children. No other vertex has more than 4 children. Next, what is the height of this rooted tree? That is the length. Height of this tree, that means height of the root. Height of the root. Height of the root means from root to the farthest leaf. So number of edges 1, 2, 3, 4, 5. So the root height will be 5. Okay, very simple. Now let's solve this question. This is an application. Okay, remember from this question you actually have to find which type of tree you will get. Can anyone tell me? Like read this question and tell me what will be the answer. This is a very simple question. So let me just short this question right now. Let's assume that you have only 8 people. Let's assume you have only 8 people. So you have total 8 people. So suppose there are 8 people, they enter in a chess tournament. Okay. Now, anyway, so now what you do? Basically, this is the hint. This is the hint that is given to you. Actually, this is the hint that is given to you. Use a rooted tree model. This is the hint that is given to you. We have to determine how many games will be played. This is what we have to do. Okay. Manideep is asking degree of tree is highest degree of node or degree of the root. That is highest degree of the node. That is highest degree. See, Manideep, tell me, is this a binary tree? Okay, Manideep, tell me, is this a binary tree? Tell me, is this, can I say this is a binary tree? Tell me, can I say this is a binary tree? Can I say this is a binary tree? The answer is yes. Yeah, yes, because binary tree means every node has at most 2 children. Okay, but you can notice what is the degree of this root? The degree, what is the degree of root? That is 1. But this vertex has degree 2. So anyway, this is binary tree. You cannot say that this is like basically degree. I can say degree of the tree. If you ask me degree of the tree, then that is basically the maximum degree of a node. Is this clear? Degree of this tree, that is basically the maximum degree of a node. Or I can say binary tree means every vertex has at most 2 children. And similarly, k-array tree, what that means? K-array tree, what that means? Okay, this is a rooted tree in which every node has how many child? Every node has at most k child, at most k children. This is the definition of k-array tree, k-array rooted tree. Every node has at most k children. Very simple. Okay. Now, what about this question? So you are in a chess tournament. There is a chess tournament. Okay. And this is the question. How many games will be played? How many games will be played? If a player is eliminated, remember a player is eliminated after one loss, and games are played until there is like I can say there is one champion. I can say there is one champion. Okay. So until there is one champion, assume there are no ties. So if you notice, what will come to your mind when you read this question? See, when you read this question, automatically what will come to your mind? automatically it will come to your mind that these are the people. So these are the 8 people. 5, okay, 5, 6, 7, 8. These are the 8 people. Okay, and you can notice one thing here. This is the chess tournament, and here, so two people will play. And read this: a player is eliminated after one loss. After single loss, after one loss, player is eliminated. After one loss, player is eliminated. So if you notice what will happen, for example, if they play a game, then one of them will go. Yes or no? If they play a game, then one of them will win. If they play a game, one of them will win. If they play a game, one of them will win. If they play a game, one of them will win. Then what will happen? Now, see, for example, here one will be eliminated. Can I say? Here one will be eliminated. Okay, here 4 will be eliminated. Here 6 will be eliminated, and here 7 will be eliminated. Okay, so now, have you seen the Squid Game? Have you seen this Squid Game? Eliminated. This Squid Game. This is a TV series. This is a web series. I think on Netflix. Squid Game. Okay. Anyway, so like after your GATE exam, you can watch. After the GATE exam, you can watch. This is a nice. Okay. After the GATE exam. Okay. So anyway, so basically they play a game and one is gone. This one is gone. This three, 4, they are playing game and 4 is eliminated. Anyway, so next what will happen? They will play a game and for example, maybe 2 can win. And they play a game, maybe 8 has won. And then finally they play a game and then finally one of them will win. Okay. So very simple. This is the idea. Now tell me one thing. If you read this question, okay, after one loss, once you lose any game, if you lose, you are eliminated. Okay, so this is the chess tournament. So what type of tree you will get? What type of tree you will get? Can you tell me what type of tree you will get for this chess tournament? What type of tree you will get? You will always get full binary tree. You will always get full binary tree. Yes or no? You will definitely get full binary tree. Yes or no? Very simple. So okay, so you can notice why you get a full binary tree. So this is your full binary tree, FBT. Because if you have, for example, if your n is even, if you have even number of people, if you have even number of people, then what will happen? Like A1, A2, A3, A4, and so on, AN minus 1, AN. Then what will happen? These two will play. These two will play one game and one of them will win. These two one will play a game and one of them will win, and so on. These two will play a game and one of them will win. Okay, and so on. So it will go on. So you can notice this if you notice, this will be actually a full binary tree. Because why this is a full binary tree? Because every node has either 0 child or 2 child. Is it possible? Like, is it possible that there can be single child? Is it possible? This is a chess tournament, so 2 people will play. Okay, like these 2 people will play, then this will be the winner. These 2 people will play, this will be the winner. These 2 people will play, then this will be the winner. Are you getting my point? So this is what I'm saying. So what you will get in this tournament, you will get a full binary tree in this tournament, because every node has 2 or 0 children. Every node has either 2 or 0 child. So you will get a full binary tree. Now tell me one thing. How many games are played? What is that equal to? Number of games played. Number of games played. That is equal to what? That is equal to number of internal nodes. Yes or no? That is equal to number of internal nodes. That is equal to number of internal nodes. For example, they will play one game. So because of them, this internal node will come. They will play one game, because of them this internal node will come. They will play one game, because of them this internal node will come. They will play one game, this internal node will come. They will play one game, this internal node will come. So number of games played, that is equal to what? That is equal to number of internal nodes. Now here, how many internal nodes you have? Internal node means a node with at least one child. A node with at least one child. So how many internal nodes we have? 1, 2, 3, 4, 5, 6, 7. So number of internal nodes is actually 7. Yes or no? So how many internal nodes you have? Total 7 internal nodes you have. Okay. So finally I can say 7 games are played. Total we are playing 7 games. Very simple. Okay. So if you have n people, tell me one thing. If you have n people, then how many leaves will be there? If you have n people tournament, n people chess tournament. You have a chess eliminating tournament. Like, okay, eliminator tournament. Like, this is a tournament you have. So tell me, how many tournament? How many leaves will be there? So this tournament, it will actually create a full binary tree. It will create a full binary tree. Yes or no? You will get a full binary tree. And how many number of leaves? What will be the number of leaves? Number of leaves will be these n people. These n people will be the number of leaves. Okay, because there are total n people. Total n people you have, like total 8 people. Here you have total 8 people. So these are the number of leaves. Okay, now tell me, this is a full binary tree, and in a full binary tree, you already know one thing. You know, in a full binary tree, you know that what we have. If you know one thing, then you know all other. For example, you know what is the number of like two children node. What is the number of internal nodes? You know, in a full binary tree, you know number of internal nodes. What is that? In a full binary tree, number of internal nodes, that is actually equal to number of two child node. Number of two child node, that is equal to L minus 1. Because in a full binary tree, every internal node has two children. Every internal node has two children in full binary tree. Every internal node, whatever internal node you take, every internal node has two children, has two child. Okay, so very simple. So this is the idea. Finally, I can say that number of internal nodes, that is same as number of games played. That is same as number of games played, and that is same as n minus 1. Okay, so these many games will be played. Okay, is this clear to everyone? So how many games will be played? These many games. So if you have 1,000 people, then how many games will be played? 999. These many games will be played. Okay, so remember, in your GATE exam, they can ask you this type of questions. They can ask you like this type of question. In this question, actually, you have to find out. See, this type of question will come in the GATE exam. You have to find out like which type of tree you like. Okay, what type of rooted tree you will get. You will get a full rooted tree. You will get a full binary tree. You will get, and in a full binary tree, you know the number of leaves. Okay, then if you know the number of leaves, if you know, then you can find the number of internal nodes. And in a full binary tree, number of internal nodes is equal to number of two children nodes. Okay, is this clear to everyone? Okay, is this clear? So okay, very simple. Give me a second. Okay, give me a second. Okay, hi everyone. Yeah, so yeah, actually in the morning, so someone has come. Okay, anyway, now this question is clear to everyone. Remember, in the GATE exam, they will not ask you a straightforward question. Like they will not ask you that there is a full binary tree, these are the number of leaves, so tell me the number of like internal nodes. This type of straightforward questions they will not ask in the GATE exam. They will give you a scenario, they will give you a situation, and from that situation you have to find out, you have to use your analytical skills. Okay, So anyway, this is a simple question you can notice, very simple. Now, can anyone tell me one more thing? Like, is there any direct way? Okay, is there any creative way to solve this question? Like, how many games will be played? Remember, every player is eliminated after one loss. After one loss, one player is eliminated. Then, how many games will be played? Actually, there is very nice method here, because tell me one thing. One game will eliminate how many? Tell me, one game will eliminate how many? One game will eliminate how many? One game basically means eliminate one. Eliminate one. Okay, eliminate one player. One game is same as eliminate one player. To eliminate one player, you need to play one game. How many players we need to eliminate? How many players we have to eliminate? These many players we have to eliminate. These many players to eliminate. We have to eliminate these many players. So how many games will be played? That is same as 999 games. So this is another way. This is another method. Yes or no? Like, this is just like very like simple. I can say only creativity, nothing else. Okay, because you know that one game. Okay, a player will eliminate after one loss. Okay, so one game means one player gone. Eliminate one player. So one game is equivalent to eliminate one player. So I can say that these many players we have to eliminate. So finally, I can say these many games will be played. Okay. Now, anyway, so this is clear. This type of questions. This is a standard application of actually. Let me tell you, this is called tournament problem. This is a standard thing. This is called tournament problem. So this tournament problem we have seen in the, okay, this is a standard problem, and in the GATE exam they will ask you the standard problems. So if this question comes, if any question comes from the tournament problem, you can solve it. Okay, let's solve this question. What do you think? Okay, what do you think? If there are two different paths, if there are two different paths between two vertices x comma y in a simple graph, then there must be a cycle. Is it true? You have two vertices, you have x comma y. If there are two different paths, if there are two different paths between x comma y, there are two different paths between x comma y in a simple graph, then can you guarantee there will be a cycle? Can you guarantee there will be a cycle? Remember, you have x, you have y. Okay, there are two different paths. Like, okay, this is your path 1, and there is another path p2. There is another path p2. Then, so because you have two different paths, now you can notice there is a cycle. You can guarantee there is a cycle. Yes or no? You can guarantee that there is a cycle. So you have two vertices x comma y. Okay, and there are two different paths between them. Then I can guarantee that there will be a cycle. Very simple. So this is your proof. Very simple. Okay. So if there are two different paths between x comma y, between some vertices, between some vertices x comma y in a simple graph, then there must be a cycle in this graph. So this type of graph must definitely, it should be a cyclic graph. Okay, very simple question. Okay, next. This question I gave you as a homework. Did you try this? I gave you this question as a homework in the last class. This is your GATE and ISRO. Actually, see, ISRO, many questions in ISRO, they are copy of GATE questions. So if you want to prepare for ISRO exam, then okay, then basically just solve the GATE exam questions and you are done. Okay, from other exams they just take. Okay, just copy paste. Now, what is the answer for this question? So remember, G is an arbitrary graph with n nodes, k components. There are total k components. If a vertex is removed from G, one vertex is removed, the number of components in the resultant graph must necessarily between what? This is the question. So remember, your graph G has k components. There are, in your graph G, there are k components. We have k components. Now we don't know what are these k components. We don't know. Okay, but we know that there are k components like G1, G2, G3, and so on, Gk. These are the k components. Now the question is saying that one vertex we remove, then what is the minimum and what is the maximum number of components that you will have? What is the minimum and what is the maximum number of components that you can have? So tell me one thing. You tell me, like, if I remove one vertex from G, if I remove one vertex, then what are the maximum number of components I can get? If I remove one vertex, Okay, so basically this is the question. What is the question? The question is asking number of components in G minus V. In G minus V, you are removing one vertex. Then what is the minimum number of components you can get? Now, very simple. If you want to get minimum number of components, let's see first maximum number of components. How many maximum number of components you can get? So this is what I want. Okay, so you have k components. Now in G minus V, what is the maximum number of components? What is the maximum number of components you can get? So for this, what you can do, if you want to get maximum number of components, for this, what you can do, for example, this type of graph you can take. You can take this type of graph where these are the single vertices. How many vertices are remaining? How many vertices are remaining? Okay, so you can notice k minus vertices are gone. Total k minus vertices are gone. Now these are the k minus vertices. These are the single vertices. Like I can say A2, A1, A2, A3, AK. So these are the k minus 1 vertices. So finally here what you can do, here you can create a star graph. This star graph you can create. What you can do, you can create this star graph. So in this star graph, tell me like total how many vertices will be there? Total you have n minus k minus 1 vertices. These many vertices you have. Now if I remove this vertex, if I remove this vertex, if I take this vertex as V, if I remove this vertex, then tell me how many in G minus V, how many components you will have? Number of components in G minus V, number of components. If I remove this, then in G minus V, number of components will be n minus 1, because all the vertices will become isolated. Yes or no? All the vertices will become isolated. So maximum these many components you can have. Is this clear to everyone? Like you can create maximum you can create n minus 1 components. Maximum these many components you can create. Is it clear? Tell me, is this clear? Did you understand this? A graph is given to you which has k components. So this graph G we have taken which has k components. And now my target is that I want to remove one vertex, but I want to get maximum number of components. By removing one vertex, I want to get maximum number of components. This is what I want to get. So I can choose this graph. This graph I can choose. Yes or no? For example, you can have G where you have like five nodes you can have, and let's assume number of components. Let's assume number of components is 3, or maybe number of components maybe, yeah, you can take as 3. Now if I want to get maximum, like in G minus V, I want to remove one vertex. And by removing this vertex, I want to get maximum number of components. Then what type of graph I will take? I want to get maximum number of components by removing one vertex. Then what type of graph I will take? This graph I will take A1, A2, A3. Remember there are 3 components. So what I can do, I can take this type of graph, A4, A5, A6. This type of graph I will take. And what I will do, I will remove this vertex. Then you can notice what is the number of components. So I will get total 5 components. Total 5 components you can get. And remember, this is the maximum. Can you do better than this? Tell me, can you do better than this? You cannot do better than this, because if you have a total, if you remove one vertex, there will be n minus 1 vertices. See, okay, if you have a graph with n vertices, like if I directly say that if you have a graph with n vertices, then what is the maximum number of component? What is the minimum number of component this graph can have? What is the minimum number of component this graph can have? Component. What is the minimum number of components? That will be 1. The minimum number of components will be 1. You make a connected graph. Okay. And what is the maximum number of components you can get if you have n vertices? What is the maximum number of components you can get? Maximum number of components, that is n. Okay, like this is your ageless graph on n vertices. Correct? Very simple. So here, after removing one vertex, this is the maximum number of components I can get, n minus 1. And tell me, Okay, after removing one vertex, if I want minimum number of components, then what I should do? If I want minimum number of components, I want minimum number of components after removing one vertex. After removing one vertex, I want minimum number of components. Then tell me what that will be. What that will be? I want minimum number of components after removing one vertex. Then what that will be? If I remove A4, will I get minimum? Tell me. If I remove A4, will I get minimum? No. If I remove A1, I will get minimum. So basically, if you want minimum number of components after removing one vertex, then remove, what you do? Remove isolated vertex. Remove a isolated vertex. Yes or no? Remove a isolated vertex. Is this clear to everyone? Just remove a isolated vertex. So if you remove isolated vertex, then I can say there will be k minus 1. These will be the number of components. This is the minimum number of components you can get. Is this clear? So the answer will be k minus 1 to n minus 1. Tell me, is this question clear to everyone? Okay. Now our next topic, that is graph numbers. What is this concept? Graph numbers. See, with every graph, there are some properties associated. With every graph, you have some numbers associated. Okay. For example, with every human, like, okay, with every human, what are the numbers associated with every human? With every human, what are the numbers associated? For example, if I ask you, what are the human numbers? Like, if I ask you, then what are the human numbers? What are the numbers that are associated with human? For example, I can say height. This is a number that is associated. Yes or no? This is a number that is associated with the human, like human body, with the human body. What are the numbers associated? I can say height is a number which is associated with human. Yes or no? Every human has a height. Okay, so I can say like this. Okay, like number of legs. Okay, like this, and so on. Okay, and so on. Are you getting my point? Number of hands, and so on. Okay, so there is height. For example, there is a weight. There is weight. Okay, and so on. So many things are there. Correct. So these are the human numbers, I can say. Similarly, with every graph, we can define some numbers which are associated with every graph. Okay, so these are some numbers that we will study. Okay, so in today's class, we will study clique and independent set. These are the main. So for today's class, so let's start with these numbers. What are these numbers? What is a clique and what is a clique and what is independent set? Before we study this, so similarly, you have graph numbers. Remember, similarly, you have a graph numbers. Graph numbers means, for example, you have something called clique number. What is clique number? What is independence number? What is independence number? This is what you have to study. Okay, like there are many others, like vertex cover number. What is a vertex cover number? What is a chromatic number? What is a chromatic number? And so on. Some more. What is a matching number? Okay, many concepts. So these are the graph number. These are the numbers that are associated with graphs. Now, before we study this, we have to study the concept of maximal and maximal and maximum. What is the difference between these two? Maximal, maximum. What is the difference? Okay, so tell me, when can you say that a set is maximal? A set is maximal. A set is maximal. When can I say this is maximal? A set is maximal with respect to some property P. With respect to property P. What it means? Some property P you have. Whether with respect to some property P. There is some property P. Okay. So when can I say that there is, like I can say, when can I say this set is maximal? A set S is maximal with respect to some property P. If okay, if nothing new can be added, if S, okay, nothing new can be added in S, nothing new, okay, nothing new can be added to S, can be added to S, can be added to S, okay, keeping the property intact, keeping the property preserved, keeping the property P preserved. This is the definition. Now with example, this concept, so basically no more elements you can add. This is the simple idea. Idea is very simple. Nothing new can be added. This is the simple line. This line is important. Nothing new can be added. No new element you can add. That is your maximal. And what is maximum? What is maximum? Like if I ask you, what is maximum? Maximum means among all the sets, what is the maximum? Like all, okay, a set is maximum with respect to property P if all other set with property P have size less than S. Yes or no? Very simple. Means this is the maximum. Maximum set S is maximum with respect to property P if all, if for all, I can say, if for all sets, if for all sets, I can say, if for all sets X satisfying property P, satisfying P, what should happen? If for all X satisfying property P, what should happen? This S is the largest. Okay, S is the largest. Okay, S is the largest. So for all, among all who are satisfying this property P, S is the largest. Let's take this example. Consider this, for example, consider these numbers like 1, 2, 3, 4, 5. Okay, and this is a property. I am giving you a property P. What is property P? This is the property P. No, I can say, what is the property P? No two elements consecutive. No two elements consecutive. No two elements consecutive. Okay, so let's take this property. This is your property. No two elements consecutive. This is your property. I'm giving you a property, and that property name is, so I can say property. Property P is no two elements consecutive. Now tell me, okay, if I ask you this question, no two elements consecutive, then in this case, can I say this set, can I say this set will satisfy this property P? This set, this will not satisfy this property P. Okay, so no two elements should be consecutive. Now tell me, can I say this will satisfy 2, 4? 2, 4. This will satisfy. Is this maximal? Can you add something? Is this maximal? Is this maximal? Can you add something? Can you add something? You cannot add something. So this is actually maximal. You cannot add anything. Just try. Can you add something? Can I add 1? Can I add 1? I cannot add 1 because 1, 2 will be consecutive. I cannot add 3. I cannot add 5. So this is maximal. Is this set, will this set satisfy the property? This set, will it satisfy the property? Yes. But is it maximal? Is it maximal? This is not maximal. This is not maximal. Can you add something? Yes. Can you add something? You can add 5. This is not maximal because you can add 5. So I can say 1, 3, 5. Is this maximal? Yes, this is maximal. And tell me, what is the maximum? With this property P, what is the maximum set you can create? With this property P, what is the maximum set you can create? This is the maximum set you can create. This is the maximum set you can create with this property P. Yes or no? So is this clear? Maximal, maximum. So remember, this set will also satisfy the property, but this is not maximal. But that is not maximal. This will also satisfy. There is no violation. Yes or no? This set will also satisfy the property. There is no violation. But this is not maximal because you can add 5. For example, you can add 5. Yes or no? This 2, 5. I can say this 2, 5. This also will satisfy. Is this maximal? 2, 5. Is this maximal? 2, 5. Is it maximal? Yes, this is maximal, right? 2, 5. This is maximal. Because you cannot add something. This 2, 5 is maximal. What about 1, what about 1, 5? 1, 5, that is not maximal. What about 1, 4? What about 1, 4? That is maximal. 1, 4 is also maximal. 1, 4. That is also maximal. But these are not maximum. 1, 4 is maximal. You cannot add something. Okay. But this is not maximum. Maximum is 1, 3, 5. This is the maximum. So is this clear to everyone? Maximal, maximum. every maximum is maximal. Yes or no? Every maximum is maximal. Every maximum is maximal. But maximal need not, okay, but maximal need not be maximum. Maximal need not be maximum. Basically, the idea is very simple. Maximal means nothing new, no new addition. No new addition possible. No new addition possible. This is the idea of maximal. And this is the idea of this largest. This is the idea of this. So the concept is clear. Maximum should be unique. Can I say maximum should be unique? Can I say maximum should be unique? For example, consider this set. 1, 2, 3, 4, 5, 6. Consider this set. And the same property you have. Your property P is same. What is the property P? The same. No two elements consecutive. No two elements consecutive. No two elements consecutive. So tell me, is maximum unique? For example, this 1, 4, 6. Is it maximal? Maximum? What is this? Like, what is this is maximal. You can clearly see this is maximal. What is the maximum you can create with this property? No two elements consecutive. What is the maximum you can create with this property? What is the maximum you can create? See, you can create, for example, 1, 3, 5. This you can create. This will be maximum because you cannot create a size 4. This is the size 3. You cannot create a size 4. This is also maximum. This is also maximum. 2, 2, 4, 6. This is also maximum. This is also maximum. Okay. So this is the idea. So remember, maximum need not be unique. Is this clear? Okay. So maximum need not be unique. Now, so this is the idea. So maximal and maximum. And what about, for example, like if I ask you 2, 5, is it maximal? 2, 5. Is this maximal? Maximal. Can you add something? Can you add something? Yes, this is maximal. But this is not maximum. Okay, very simple. So these are the concepts: maximal, maximal, maximum. Now let's see the concept of clique and independent set. What is a clique? What is independent set? First, let's see the definition. And these are actually very simple, and these are completely extreme of each other, extreme opposite of each other. For example, if I give you a graph A, B, C, D, E. Okay, let us assume that you have this graph. Okay, and so on, like this is your graph. Now in this graph, what is a clique? Let me tell you what is a clique. Clique is basically, clique is a subset in which every two elements are adjacent. Clique is a subset in which every two elements are adjacent. For example, look at this. A comma B. Is this a clique? A comma B. Is this a clique? Every two are adjacent. Every two are adjacent. This is a clique. For example, B, E, D. Is this a clique? Is this a clique? Every two are adjacent. Yes, every two are adjacent. Tell me, is this a clique? C comma C, D, E, A, D, E. Is this a clique? A, D, E. A, D, E. Is this a clique? No, because A comma E are not adjacent. They are not adjacent. Okay. So clique means a subset in which every two elements are adjacent. Yes, complete subgraph. Basically, clique means what I can say. Clique is basically complete subgraph. Subgraph which is complete. Clique is basically a subgraph. This is a subgraph which is complete. Which is complete. Which is complete. Complete means every two elements are adjacent. See, this is not a clique. Why this is not a clique? Because A comma E are not adjacent. They are not adjacent. This is a clique because they are adjacent to each other. And what is independent set? Independent set. What is an independent set? This is, name itself is telling you. Name itself is telling you independent of each other. It means every two elements are non-adjacent. Every two are non-adjacent. Every two non-adjacent. So tell me, is this a clique? Is this an independent set? Every two are non-adjacent. Yes, this is the independent set. Is this an independent set? Yes, no problem, no problem. Okay, now see this A comma D comma E. Is this independent set? Independent set. No, this is not independent set because they are adjacent. Because these two are adjacent. So the definition is clear. Independent set. The name itself is telling you independent of each other. Independent of each other means, okay, independent of each other means, it means simply they are non-adjacent, pairwise non-adjacent. They must be pairwise non-adjacent, and here you should have pairwise adjacent. So the difference of clique and this is this clear? Clique and independent set. The difference. A comma D. A comma D, is that independent? Yes. Yes, A comma D is independent set. A comma D, this is independent set because they are not adjacent. They are not adjacent. See the definition. Please understand the definition, because if you understand the definition, you have cracked GATE exam. Many times I tell you this. Okay, at least 100 times I have told you this. If you understand the definition, you are done. Okay, you have done it. So let's see the definition of clique. What is the clique? Clique is a subset which is pairwise adjacent vertices. Remember, clique is a pairwise adjacent set. I can say set of pairwise adjacent vertices. Means every two people are adjacent. This is called clique. And the size of maximum clique, that is the clique number. What is the clique number? That is the size of maximum clique that you can create. And this is the symbol for clique number. And what is independent set? Independent set means pairwise non-adjacent vertices. So you can notice here you have pairwise adjacent and here you have pairwise non-adjacent. Okay, so this is called independent set, or I can say stable set. Stable set. The size of maximum independent set, that is called independence number, or I can say stability number, and the symbol is alpha of G. This is the symbol for maximum independent set. With example, this concept will become more clear. So let's take the example. Consider this example. A, B, C, D. This is your graph. Okay, and let's assume there is some E. This is your graph. Now in this graph, you tell me what are clique. In this graph, you tell me, okay, so I am asking you what is a clique. What are the clique? Remember clique means, remember the definition. Clique means pairwise adjacent. Every two must be adjacent. Clique means pairwise adjacent. Pairwise adjacent vertices. Pairwise adjacent vertices. Every two must be adjacent. So that is your clique. So tell me, is this a clique? For example, if I give you BD, is this a clique? B comma D. Is it a clique? Yes, this is a clique. Pairwise adjacent. Is this a clique? This B, is this a clique? Yes, there is no problem. There is no problem. Pairwise adjacent vertices means distinct vertices, they should be adjacent. Like here you have pairwise adjacent. There is no violation here. We don't have any violation. Okay, next, what about this B comma C comma E? What about this? This is not a clique because B comma E, they are not adjacent. So, sorry, C comma E, they are not adjacent. So this is not a clique. Tell me, BDE, BDE, is this a clique? Yes. Is this maximal? Can I say this is maximal clique? Can I say this is maximal clique? Can you add something more? Can you add something more? No, you cannot add something more. This is the maximal clique. You cannot add something more. Is this a clique? Tell me. Is this a clique? Is this a clique? No, because you can notice E comma A, they are not adjacent. So this is not a clique. This is not a clique. Is this a clique? Is this a clique? Yes, you can notice that this is a complete subgraph. Clique means complete subgraph. Okay, you can notice here every two people are adjacent to each other, pairwise adjacent. Every two people adjacent. So this is a clique. This is a clique, pairwise adjacent. So this is a clique, but this is maximal clique. This is not maximum. Yes or no? This is not maximum clique. This is not maximum clique. What is the maximum clique? I can say A, B, C, D. This is the maximum clique. This is your maximum clique. You cannot create anything more than this. can you create a clique of size 5? Can you create clique of size 5? Like, is this a clique? No, this is not a clique. So finally, what is the clique number? What is the clique number? Finally, what is the clique number? Clique number means omega. Omega of G. This is your G. Clique number is 4. Clique number is 4. Because clique number means the size of maximum clique. The size of maximum clique. So omega of G is 4. Is this clear? For example, this is this maximal? Is this maximal? This is not maximal. This is not maximal because you can add E. In this, you can add E. You can also add C. For example, this is a clique. Yes or no? BCD. This is a clique. This BCD, I can say. This BCD. This is also clique. Okay. This BCD. This is a clique. So remember, a clique is basically, what is a clique? If you notice, this is very simple to observe. What is a clique? In a clique, you have every two vertices are adjacent. This clique is a subset of vertices, a subset of vertices, a subset of pairwise adjacent vertices. I can say a subset of pairwise adjacent vertices. Okay, this is your clique. Now, when every two pairwise adjacent, what this means? It simply means that pairwise adjacent. It simply means that it will be a complete sub. It means it should be a complete subgraph. It will be a subgraph which is complete. It will be a subgraph which is complete. Means subgraph which will be complete. Subgraph which is complete. Okay. Is this clear? So this will be a subgraph which is complete. It will be a subgraph which is complete. It will be an induced subgraph which is complete. Induced subgraph, you will get an induced subgraph which is complete. Yes or no? Very simple. For example, here, like this, like I can say this is a clique because this is a complete subgraph. This is your K4. This is your K3. So this is also max. This is also clique. This is K3. What is this? What is this? This is your K4. This is your K3. What is this? This is your K2. This is your K3. This is your K1. But this is not K5, right? This is not K5. Okay. So this is the idea. Now let's see the independent set. Now let's come back to independent set. Independent set means pairwise non-adjacent. It simply means pairwise non-adjacent. Pairwise non-adjacent vertices. Pairwise non-adjacent vertices. This is your independent set. So tell me, can I say this is independent set? Can I say this is independent set? Yes. Yes, no problem. There is no violation here. We have no violation here. Okay, tell me, what is the maximum independent set you can create? Create the maximum independent set. What is the maximum independent set you can create? Can you create the maximum independent set? Let's create the maximum independent set. How many you can take from this? If you want to create maximum independent set, how many you can take from this? Only one, because they are pairwise adjacent. You can only take one of them. For example, I can take A, E. Nothing else. So this is your maximum independent set. Maximum. This is also maximum independent set. Okay. So what is the independence number? Alpha of G, that is 2. Alpha of G is 2. Okay. Clear? Is this concept clear? Independent set. So the definition, a set of vertices is called independent when no two vertices are adjacent. When no two vertices are adjacent. Similarly, this is the definition of independent set. Means no two vertices are adjacent. No two vertices adjacent. And what is a clique? Clique means every two vertices are adjacent. Okay, independent set is maximal. Means you cannot add something more. Maximum independent set and maximum clique number. So remember, this is what alpha omega of G. This is the clique number. This is the clique number. And what this means? Clique number is same as, I can say, size of maximum clique. I can say size of maximum clique. Or I can say size of maximum, I can say size of maximum complete subgraph. I can say size of maximum complete subgraph. Yes or no? Size of maximum complete subgraph. In a maximum complete subgraph, what you largest sub, I can say the number of vertices in largest complete subgraph that you can create. This will be your clique. Yes, single vertex is clique because there is no violation. Single vertex is clique. Okay. Priyanshu is asking, clique number plus independent number, is this equal to order? No, Priyanshu, you can see in this example. In this example, you can notice the clique number is actually 4. The clique number is 4. The independence number is 2. The total is 6. The total is 6. So this statement is not true. Okay. So this is your clique number. Clique number is, this is the idea. Clique number means size of maximum clique. Size of maximum clique. This is your clique number. I can say size of largest complete subgraph. This will be your clique number. Next, what is the concept? That is alpha. What is alpha? What is alpha? This is your independence number. And this is size of maximum independent set. Okay. Now let's see. So what is independent set? You can notice from this. So what is, for example, this is the independent set. For example, this is an independent set. Correct? Yes or no? For example, okay. So this is the idea. This is the definition of independent set. Like here, you can notice this is an independent set, right? Yes or no? This vertex in this graph, this is maximal. Can I say this is maximal? Can I say this is maximal? This vertex, if I take this vertex, can I say this is maximal? Yes, this is maximal. You cannot add something more. This is the maximal independent set. So I can say this is the independent set and this is actually maximal. This is actually maximal independent set. And if I take these two vertices, this will be the maximum. Actually, in this graph, what is the maximum independent set you can create? What is the maximum independent set you can create in this graph? Maximum. That you can create only 2 vertices you can take. See, you cannot take 3 vertices. Whatever 3 vertices you take, with this vertex, you cannot take anything else. With this vertex, you cannot take anything else. Now, what I have to do, if I want to create a maximum independent set, I cannot take this vertex, because if I take this vertex, I cannot take anything else. So this vertex is out of picture. We don't, okay, this vertex is gone. From the remaining vertices, you can take only 2 vertices you can take. Yes or no? So this is the maximum independent set. So for this graph, what is the alpha of G? What is the alpha of G? That is 2. Alpha of G is 2. Now tell me the omega of G. For this same graph, what is the omega of G? For the same graph, like what is omega? Omega of G. What is the largest clique you can make? Okay, just focus on what is the largest complete subgraph you have. See this K3. This is the largest complete subgraph you can create, K3. Can you create K4? Do we have K4 here? Do we have K4? In this graph, do we have K4? Is there any K4 in this graph? We don't have any K4, right? In this graph, you can check there is no K4, but we have K3. We have K3. So I can say in this clique number will be 3. Is this a clique? Is this a clique? Yes, this is a clique. There is no problem. Remember, yes, this is a clique. This is a clique, but this is not maximum. I can say this is your maximum clique. This is your maximum clique. So the clique number is actually 3. Okay. Like, okay, this independent set, have you seen this in the practical life? This independent set, have you seen this in your practical life? Like the exam hall, you can notice. In the exam hall, you can notice what they do. In the exam hall, they try to, like, okay, they try to put the people from the different branches. For example, let's assume these are the mathematics people. These are the mathematics people, M1, M2, M3. These are the mathematics people. Okay, and these are the chemistry people. Let's assume these are the chemistry people, C1, C2, C3. Then what in the exam hall, what will happen? In the exam hall, what they will do? They will make sure that on one table, there is, let's assume this is a table. They will make sure that on one table, adjacent people are not there. Yes or no? They will make sure on one table, adjacent people are not there. Means on one table, what you should have? On one table, what you should have? Pairwise non-adjacent. So something like this. Pairwise non-adjacent people. So like this. So in this, like this, you can, okay, this is just an analogy. This is a practical analogy if you want. Practical analogy of, okay. So here you can notice, for example, suppose there is a graph in which vertices are a student in a class, edges are basically friendship. Now, what is the maximum number of students you can put in an exam room if no two friends should be there? Tell me, if no two friends should be there, then what is the maximum? Like, what is the maximum number of people you can put in an exam room, in a room, so that no two friends should be there? Like, this is your question. What will be the answer? A graph is there. In this graph, there are students. Like, these are the students, A, B, C, D, E. Let's assume these are the students. And the edges are friendship. The edges are friendship. For example, maybe this is your graph. This is the graph. Let's assume this is your graph. Now, what is the maximum number of students you can put? What is the maximum number of students you can put so that no two friends should be there? No two friends should be there. What is the answer? What is the answer? The answer is actually independence number. The answer is your alpha of G. For this question, the answer will be alpha of G because no two friends should be there. So very simple. So actually, for this question, what is the alpha of G for this graph? What is the largest independent set you can create? The independent set, the maximum independent set that you can create. What is the maximum independent set you can create? In this maximum, what you can create? So for example, you can take B, you can take, okay. See, if I take B, then can I take something else? Like what, if I take B, then 2, size 2 I will get. So what should I do? What should I do? I can take CDB. This is what I can do. Yes. So this is the maximum independent set you can create. This is the maximum. Remember, B comma C, this is maximal. Sorry, no, this is not maximal. This is not maximal. I can say B comma D. No. B comma E. Yes. B comma E is maximal. You can notice. B comma E, that is actually maximal. So the maximum, so the alpha of G, that will be 3. Is this clear? So actually for this question, answer will be in maximum independent set. What is the answer for this question? What is the stability number? Stability number means independent number. That is simply independence number. Stability number means independence number. That is the maximum possible size of an independent set in a graph. So for this graph, can you notice what is this graph? Can anyone notice what is this graph? This looks complicated, but actually this is your cycle graph. This is actually your C6. This is your C6. So in this C6, tell me, what is the in this C6, what will be the independent set in this C6? So if you have this C6, okay, like this is your C6. In this C6, what will be the independent set? A, B, C, D, E, F. Then what will be the alpha of G? Alpha of G will be 3 because you can take these 3 vertices. Like you can take A. Now you cannot take B comma C. If you take A, you cannot take B comma C. You can take D, you can take E. This is a maximum independent set. Or you can take B, C, F. This is the maximum independent set. Okay, so this is the idea. Very simple. Like for example, if I take A, I cannot take B comma C. And if I take F, then tell me, is this maximal? Is this maximal? Yes, this is maximal. This is maximal, but this is not maximum. So this will be the answer. So for this question, answer will be what? Answer will be 3. And for this question, what will be the clique number? What will be the clique number for this cycle? What will be omega of g? Clique number. What is the largest complete subgraph you have? That is 2. The largest complete subgraph you have is K2. This K2 is the largest complete subgraph that you have. Okay, so very simple. Now, in a cycle graph, let's do the analysis of cycle graph. If you have a cycle graph, like Cn, then for Cn, what is the alpha of Cn and what is omega of Cn? What is alpha of Cn and what is omega of Cn? Tell me. First, let's see alpha of Cn, means independent set. So for a cycle graph means n is greater than equal to 3. You know, n is greater than equal to 3 because I told you that cycle graph starts from 3 vertices. So what is the alpha of Cn? Just check it. So for alpha of Cn, see, if n is odd and if n is even. So for example, if you have this, then what is the alpha here? What is the alpha here? That is 2. You can take these 2 vertices, you can take. If this is the case, then what is the alpha? That is 1. For this graph, alpha is 1 because the independent set, that will be 1. Only one vertex you can take. And if you have 5 vertices, then you can take alpha will be 2. Alpha will be 2. For example, if you take this vertex, then you have to take one of them. So this alpha will be 2. And if you have C6, then alpha will be 3. If you have C7, then alpha will be 3. C8, alpha will be 4. C9, alpha will be 4. Are you getting this point? So very simple. So you can notice. Okay, like here, C4. Okay, so what is the answer here? So I can say answer will be n by 2. So when you have even, when your n is even, then you can directly say n by 2. And when your n is odd, then I can say n by 2 floor. Actually, okay, you can combine these two and you can finally say that okay, so this will be the answer. Now when n equal to 3, then your answer will be 1. You can put n equal to 3. If you put n equal to 3, then what you will get? You will get 1. So this is the answer. You can combine these two. Actually, you don't have to do this. What you can directly say the answer will be n by 2 floor. Whatever graph you have, just do n by 2 floor. Just directly write n by 2 floor. Okay, so very simple. Now let's see the next one. This omega. Let's see the omega for Cn. What is the omega for Cn? What will be the omega? See, omega will be what? Omega means largest clique. What is the largest clique you can create in a Cn? So for example, if your Cn is this, then what is the omega? Then the omega here is 3 because this is the complete subgraph. Omega here is 3. But if you have this, then what is the omega? Now omega is 2. If you have this, now what is the omega? The omega again is 2. So whatever you take, now if you have this, then what is the omega? Omega will be 2. So whatever you do, omega will be basically 2. I can say omega will be 3 if when n is equal to 3. And for n is greater than equal to 4, omega will be 2. The largest complete subgraph that you can create. So you can notice here in this, the largest complete subgraph I can create is K2. This K2 I can create. In this, the largest complete subgraph, that is K2. Okay, very simple. Now, one more. Let's do the analysis for complete graph. For complete graph, what will happen for complete graph for Kn? What will happen to the alpha of Kn? What is the alpha of Kn? Complete graph. Only one vertex you can take. Yes or no? Because every 2 vertices are adjacent. So alpha, independence number, the largest independent set you can create is size 1. You cannot take 2 vertices. Yes or no? Independent set, you cannot take 2 vertices because every 2 vertices are adjacent. And what is the omega of Kn? that is n. Omega of kn is n. Okay, next let's do for path graph. For path graph, what will happen? What will be the alpha of path graph and what will be the omega of path graph? First you tell me omega. This is easy. For a path graph, what is the omega? Omega is actually 2 when n is greater than equal to 3. Sorry, when n is greater than equal to 2. When n is greater than equal to 2, then omega will be 2 because you have a path graph. So in a path graph, what is the largest complete subgraph I can create? This is the largest complete subgraph I can create. This is the largest complete subgraph. And when your n is equal to 1, then it will be simply 1. What about alpha? What about alpha? This alpha, what this will be? For example, in this, what is the alpha? In this, what is the alpha? Alpha here is 3. In this graph, the alpha is 3. So what will be alpha? For example, if you have this, then what is the alpha? Here alpha is 1. And if you have this, then alpha will be 2. And if you have 4, then alpha will be 2. Here also alpha will be 2. And if you have 5, then alpha will be 3. You can take these 3 vertices, you can take. Okay, and in P6 also alpha will be 3. Okay, so just try it. Okay, let me give you a question. You check for Pn and you also check for Q this. In for this Qn also you try. Okay, let me give me 1 second. Okay. Okay, so hi everyone. Now, what is the alpha of Pn? So what you can say, like for P6 also alpha is 3. So the answer is actually, what is that? That is seal. That is n by 2 seal. It will be the answer. Yes or no? N by 2 seal. You can check. For example, when you have P5, then alpha is 3. P6 alpha is 3. Okay, so the answer will be n by 2 seal. Now you can put n equal to, for example, if you put n equal to 3, then the answer will be, if you put n equal to 3, answer will be 2. Answer should be 2. Okay, if you put n equal to 2, if you put n equal to 2, answer will be 1. That is fine. Okay, very simple. So the answer will be n by 2 seal. This will be your alpha. Now let's see. So what is the independence number of, what is the independence number of Kn? That we already know. For Kn, the independence number will be 1. For Cn, the independence number will be n by 2 floor. For Qn, first you tell me for Kmn. What is the answer for Kmn? For complete bipartite graph. This Kmn, this is your complete bipartite graph. So in this, what you can do, very simple. See, this is your complete bipartite graph. For example, this is your K34, like A, B, C, okay, like 1, 2, 3, 4. So you can notice this is a complete bipartite graph. So what is the independent set? See, this will be the independent set because they are non-adjacent. This also will be independent set. They are non-adjacent. So the largest independent set that you can create, that will be max of m comma n, because this is the largest you can create. Remember, okay, remember, tell me one thing. If I take this, then can I take something from here? This is a complete bipartite graph. Means every vertex here is adjacent to every vertex here. Okay, every vertex here is adjacent to every vertex here. So this is the idea. Now you can clearly see that the I can say this independence number, that will be the maximum of m comma n, because this part will be independent set Remember this complete this part. This part is also independent set. This part is also independent set. The largest independent set will be, this is the maximum independent set. This is the maximum independent set. Very simple. And what about Qn? Can anyone tell me what about Qn? We have already seen. Remember, Qn. Qn is a bipartite graph. Yes or no? You already know Qn is a bipartite graph. This we have already seen. Qn is actually a bipartite graph. Okay. So what are the two partition? What are the two partition? Odd parity, even parity. Odd parity, even parity. Hypercube. Yes. This is the hypercube graph. This is your hypercube graph. This is bipartite. Yes or no? Every hypercube graph is bipartite. Preeti, we have already seen this. This is your hypercube graph. And hypercube graph is actually bipartite. This hypercube graph is bipartite. So you have odd parity, you have even parity. So here you have, for example, odd parity strings. Here you have even parity strings. Okay. So you can notice that this will be the independent set. Yes or no? This will be the independent set. This will be the independent set. Correct? This will be independent set, and this also will be independent set, because this is bipartite graph. Odd parity, even parity. These are non-adjacent. These are non-adjacent. Tell me, what is the cardinality of this? Like, how many we have here? Odd parity. Half of them. Yes or no? Half of them. Here also, how many we have? Half of them. So the answer will be what? What is the independence number of Qn? What is the independence number of Qn? For Qn, what is the independence number? That will be 2 power n minus 1. Because half. This will be the independent set. Yes or no? Is this clear to everyone? For Qn. Because we already know that this QH is bipartite. This we have already seen. Okay, because the two partition you have, partition into vertices that have odd and even number of ones, odd parity, even parity. And okay, and this because you have bipartite, so I can say every partition. So there will be two partitions. There will be a odd parity partition and there will be even parity partition. So in this odd parity partition, you have 2 power h divided by 2. You have QH. Okay. So these many vertices will be there. In this even parity partition also 2 power h divided by 2. Half vertices will be here. Half vertices will be here. And you can notice, because this is bipartite, so there is no edge here. So this is actually your independent set. This is your independent set. This is also your independent set. Is this clear to everyone? So the independence number will be actually 2 power h minus 1. This will be your independence number. Is this clear? Let me know. All these concepts we have seen. The complete analysis of all these things. This is your UGC NET question. UGC NET 2016. What is the answer? Read the definition. A clique. Read the definition. A clique is simple undirected graph. A clique in a simple undirected graph is a complete subgraph that is not contained in any larger complete graph. Can anyone tell me from this definition what this clique means? Is this the definition of clique that we have seen? Is this the definition of clique we have seen? This is not the definition of, this is the definition of maximal clique. This is the definition of maximal clique. Remember, this is the definition of maximal clique. This is actually the definition of maximal clique. Definition of maximal. Because what is the definition of maximal clique? You just think about it. Like, for example, if I give you this graph, A, B, C, okay, and so let's assume this is your K4 and this is your graph. Now tell me one thing. Read this definition. This definition is saying that a clique is a complete subgraph. A clique is a complete subgraph. So take this. This is a complete subgraph. So far, so good. So far, it is good, right? So a clique is a complete subgraph. So you can notice this is a complete subgraph. That is fine. That is not contained in any larger complete subgraph. Tell me, is this contained? Is this contained inside a larger complete subgraph? Tell me, is this contained in a larger complete subgraph? So yes, this is your, so according to this definition, you can notice this is a clique. You can notice this is a clique. You can also notice this is actually maximal clique. Maximal clique. Okay, because you can notice maximal clique means not contained in any larger complete subgraph. In any larger complete subgraph. That is the definition of maximal clique, not the maximum clique. Is this clear? This understanding is very important in the exam. When you see this statement, then you should think that you should find that this is the definition of maximal clique. This is not the definition of maximum clique. This is the definition of maximal clique, and this is important. Okay. What is the doubt, Nikhil? See, this is a clique. Can you say BCE? Tell me one thing. Is this maximal clique BCE? Now tell me one thing. Tell me, because you cannot add something. Is this contained within another? For example, like A. Take this example. A, B, C, D. Okay. Now, in this graph, tell me, is this the clique? Tell me, is this a clique? Is this a clique? Is this a maximal clique? Tell me one thing. Is this a maximal clique? No, this is not a maximal clique. But this is a clique. You can notice this is a clique. See, this is a clique. This is a complete subgraph. Tell me, is this contained in another? Is this contained in another larger complete subgraph? Is this contained in larger complete subgraph? Yes, this is contained in this subgraph. You can notice this is contained in this complete subgraph. So I can say this is clique, but not maximal clique. But not maximal clique. This is not maximal clique. Why this is not maximal clique? Because this is contained in another larger complete subgraph. Is this clear to everyone now? Please tell me. Now is it clear? So this is a clique, but this is, you can notice that this is contained. I can say this is contained. This is contained within larger complete subgraph. Within larger complete subgraph. So because it is contained within larger complete subgraph, so it is not maximal clique. The same thing you can say for this. The same thing, what you can do, you can say the same thing for this. So this is your graph. Now in this graph, if you notice this, just notice this one. Is this a clique? This BCD. Yes, this is a clique. Can I say this is contained in another larger complete subgraph? Is this contained in another larger complete subgraph? Yes, this is contained. You can notice this is contained in another larger complete subgraph. So this is a clique, but this is not maximal clique. But you can notice this is clique also, maximal clique also, because this is not contained. This is not contained in another larger complete subgraph. You can notice this is not contained. Yes or no? This is not contained in any larger complete subgraph. So is this question clear? Please tell me. From the question you have to understand. So in this question the definition is given, but see, the question is using this word clique, but actually what he means maximal clique. Remember, this is the trick. This is the trick in this question. This is a beautiful question, because in this question he is using the word clique. This clique word he is using, but the definition is actually the maximal clique. So actually this definition is not of a clique. This is not a definition of clique. Remember, this is not a definition of clique. This is not a definition of maximum clique. So what is the definition? This is the definition of maximal clique. This is the definition of maximal clique. Now tell me the answer. How many maximal cliques are there? How many maximal cliques we have in this graph? Total, how many maximal cliques we have here? Maximal. Total, how many maximal cliques we have in this graph? What is the answer? This is actually a very beautiful question. So can you notice one more thing? Can you notice? Tell me, is this maximum? Is this maximal? First, to tell me, is this maximal clique? Is this maximal clique? This is not even a clique. This is not even a clique. This is not complete. Array, this is complete. Array, this is K4. This is K4. This is not complete subgraph. This is not complete subgraph because you have this vertex. This is complete. There is no vertex. Here there is no vertex, but here we have a vertex. This is a very nice question. Are you getting? Are you getting that this is not a clique? This is not a complete subgraph. This is not a complete subgraph. Okay. So finally answer will be what for this question? Remember, this is not a complete subgraph. So for this question, the answer will be, you want maximal clique. You want maximal clique. So I can say answer will be, this will be the answer. Okay. This will be the maximal clique. So I can say this will be a maximal clique. What you can do? You can create this. This will be the answer. And also this will be the answer. This will be the answer. So 4 you can create in this. So total answer will be 5. Answer will be 5 because you can create this triangle like ABG. So basically I can say ABG, this will be a maximal clique. I can say BGE, this is a maximal clique. DGE, maximal clique. AGD, this is maximal clique. And also BEF, BEFC, this is maximal clique. So total 5 maximal clique you have. Okay, is this clear? One last thing, let me just tell you, last thing. What do you think? Okay, if you have a, in G, the clique you have. So let's assume you have a clique. Clique in G, you have a clique in G. You have a clique C in G. Okay, what it will become? What it will become in G complement? In G complement, what it will become? This C is a clique in G. What it will become? This C, what it will become in G complement? It will become independent set. Very good. It will become independent set in independent set. It will become independent set. This C will become independent set in G complement. Why? See, because it is a clique in G. Okay, you have this graph G. Let's assume A, B, C. This is your graph. Okay, now this is the graph. So you can notice that in this graph, this is a clique. A, B, C. This is a clique in this graph. In this graph, this is a clique. Now, what is the G complement? What will be the G complement? A, B, D, C. In G complement, these edges will be gone. These will be gone. See, here you have pairwise adjacent. These are pairwise adjacent. Pairwise adjacent. So in the G complement, these edges will be gone. These edges will be gone. So they will become pairwise non-adjacent. Pairwise non-adjacent. So what you will get actually, this is your G complement. DC, DA. This will be the G complement, yes or no? This will be your G complement. So in this G complement, can you notice this A, B, C? This is an independent set. This is an independent set. So this is the idea. Very simple. So finally, I can say if you have a clique C in G, then in G complement, it will become independent set. Similarly, if you have independent set, then it will become a clique. Yes or no? If you have independent set in a graph, then in the complement, it will become clique. Very simple. In the complement, like here, you can notice that this BD, this is an independent set. This is an independent set here. In the complement, it will become a clique. So finally, what I can say, or if you tell me one thing, if you have maximum independent set, if you have, let's assume you have S. Let's assume S is maximum independent set. Maximum independent set in G. In G. Then tell me what it will become in G complement. Then this S is what? This is maximum independent set. So this will be clique. This will be the maximum clique. This will be the maximum clique in G. Okay. So remember, if S is maximum independent set in G, then it will become maximum clique in G. And if S is maximum in G complement, sorry, in G complement, Okay. So this will happen. Yes or no? Very simple. Is this clear to everyone? Because if you have maximum independent set, see, it will become a clique, but how can you guarantee it will be maximum? See, if S is maximum independent set, my question is this: if S is maximum independent set in G, because it is independent set, so in G complement it will become, so S is a clique. You know it will become a clique. You already know it will become a clique because here you have independent set. So this S will become clique in G complement. But how can you guarantee that it will be the maximum clique? In this G complement, can we have bigger clique than this? In G complement, can we have bigger clique than S? This is my question. In G complement, can we have bigger clique than S? My question is this: can we have bigger clique than this in G complement? What is the reason? Can anyone tell me? In G complement, can we have bigger clique than S? What is the reason? Do by contradiction. If we have bigger, assume there is a bigger clique. Assume there is a bigger clique. Okay, assume there is a bigger clique. Assume there is a bigger clique. Assume there is a bigger clique than S. Okay, in G complement, you have a bigger clique in than S. You have bigger than S in G complement. Then this bigger clique you have, for example, let's call it this bigger clique M you have. This bigger clique M you have. Then tell me how to get contradiction. If you assume there is a bigger clique, are you understanding the question? See, this S is a maximum independent set. Because this is independent set. Independent set means pairwise non-adjacent. So the vertices in S, they are pairwise non-adjacent. So in the G complement, they will become pairwise adjacent. So in the G complement, they will become clique. My question is, this S is maximum independent set here, but can I guarantee that this will be maximum clique? So in G complement, can we have bigger clique than S? Can we have bigger clique than S? Now you can notice that, assume there is a bigger clique than S. Assume there is a bigger clique than S. Now what will happen? If there is a bigger clique than S, then in G what will happen? Tell me, in G what will happen? This M will be what? This M will be what? This M will be independent set. Yes or no? This M will be independent set. And you can notice this M will be independent set and M has size greater than S. So there is a contradiction. What is the contradiction? And what is the contradiction? So in G, M will be the independent set and M is greater than S because M is bigger than S. So there is a contradiction. What is the contradiction? The contradiction is because we are assuming that S is the maximum clique. S is the maximum independent set. So there is a contradiction. What is the contradiction? Contradiction is this: we are assuming S is maximum independent set. The contradiction is S is maximum independent set. This is what S is maximum independent set. So this is the proof by contradiction. Is this clear? Very simple. The idea is like this. In graph G, you have maximum independent set, maximum, largest independent set. Okay. Then independent set means pairwise non-adjacent. They are pairwise non-adjacent. So in G complement, they will become pairwise adjacent. So in G complement, they will become clique. Now in G complement, this S is a clique. But in G complement, can we have a bigger clique? In G complement, can we have a bigger clique? So if you notice, if we have a bigger clique in G complement, then that bigger clique will become independent set in G. So in G, we will have a bigger independent set, and that is the contradiction, because we are already saying that S is the maximum independent set. So this is the final conclusion. So if S is the maximum independent set in G, then it will be the maximum clique in G complement. And if S is the maximum clique in G complement, then it will become maximum independent set in G. Is this concept clear? Please tell me. Is this concept clear? The same thing will happen for maximal. The same thing will happen for maximal. The same thing will happen for maximal. Okay. All these concepts, are they clear? Please let me know. So this is enough for today. So we have seen independent set and this clique and independent set. Like, are you confident that you understood? Did you understand the definition? Did you understand the comparison? Okay, like maximal, maximum, what is the clique, what is the like largest clique number, independence number, largest independent set. So all the concepts that we have seen. Okay, what is the alpha and gamma, what is the alpha and omega in path graph, cycle graph, complete bipartite graph. Okay, so everything we have seen, hypercube graph. So this is the complete analysis. So before going, can we solve this question? Can we try this question before going? Independence number we have to find for G1 and G2. So for G1 and G2, let's find the independence number. First, for G2. For G2, what is the independence number for G2? G2 bhaiya. You know G2 bhaiya? There is a quota factory. Anyway, so let's see this. So what is the independence number of G2? So in this G2, this is a path graph. You already know this is a path graph. Tell me, this is your 1, 2, 3, 4, 5, 6. This is your P6. So the answer will be directly 3. You can directly say answer will be 3 because this is a path graph. So the answer will be what? So the answer will be seal. The answer will be seal 6 divided by 2. Seal 6 divided by 2. This will be the answer. Answer will be 3. Okay. This is the answer. And what is the omega? What is the omega of G2? For this G2, what is the omega? Omega is 2. Omega, the largest complete subgraph. The largest complete subgraph that you can create. Largest, maximum clique, maximum. Okay, so that is your K2. What about this G1? What is the alpha of G1? Alpha of G1. Tell me one thing. If I take this vertex, can I get maximum? Like if I take this vertex, can I take something else? If I take this vertex, can I take anything else? If I take this vertex, I cannot take anything else. So this vertex you cannot put in the maximum independent set. If you want to create maximum independent set, you cannot take this. So this is out of the picture. This is out of the picture. So what is the maximum independent set you can create? What will be the maximum independent set you can create? So this is out of the picture. You cannot take this. So what I can take? I can take, for example, I can take V1, then I can take V5, I can take V2. So actually I can take V1, I can take V2, I can take V1, V2. So can I create like, okay, can I create size 4? Can you create size 4 independent set in this? Can I create size 4 independent set? This is out of the picture. You don't have to worry about this. So can we create size 4 independent set? If I take this, then I can take this, then I can take this. So I think we cannot create size 4. Yes or no? We cannot create size 4. So the independence number will be 3. There is no size 4. You can try, like you can check. Whatever you try, if I take V1, see, if I take V1, then what is the largest I can create? If I take V1, I cannot take V6. Now from the remaining four, I can take two only. From the remaining four, I can take these two. If I take this, then I yeah, okay, so 2i. Okay, so I think there will be only three. What is the omega? What is the omega of G this? So independent set, the largest independent set you can create, for example, V1, you can take V2 and you can take V5. Okay, so like this you can do. And what is the omega? The omega is 3 because you have a triangle. So like you have a triangle. Do you have K4? In this, do you have K4? Like, can you find K4? Do we have K4? Do we have K4? There is no K4, right? We don't have any K4. So the omega will be 3 and alpha also will be 3. Okay, so this is the simple question. What is the independence number of this graph? Tell me, what is the independence number of a graph on n vertices? Every two vertices are connected by A's. Connected by A's. So this is your complete graph. This is the complete graph on n vertices. The independence number will be 1. And what is the answer for this? So alpha will be 1. You can notice the alpha will be 1 and omega will be what? Omega will be n. Independence number of a graph with at least 3 vertices and only one edge. What is the answer for this? At least 3 vertices and only one edge. There is only one edge and at least 3 vertices. Like you have at least 3 vertices. So for example, you have n vertices and only single edge. Single edge you have. And where n is greater than equal to 3. This is the question. This is your part C. So you have total n vertices like A1, A2, A3, A4 and so on. Total n vertices you have, and there is only one edge. Then for this graph, what will be the alpha? The alpha will be, you can take all these vertices and you can, so basically you can take all these vertices. So the alpha will be n minus 1. Alpha, that will be n minus 1. This is the largest independent set you can create. And what is the omega? The omega will be 2. The omega will be 2. You can create K2. Okay, so very simple. So this is the answer for this question. So for this question, answer will be n minus 1. That will be your alpha and omega will be 2. Okay, very simple. So in the next lecture, we will study, in the next class, we will study vertex cover, edge cover, covering number. This concept we will study in the next class. Okay. So this type of questions they can create in the exam. Like this is a university question, you can notice. Okay. So that is enough. Now, okay. So see you tomorrow. Thank you, everyone. If you have any doubt, please ask. Don't keep any doubt. Whatever doubt you have, ask. Did you understand everything in today's class? Please let me know. After every class, you should let me know. Did you understand everything? We have done the complete analysis of independent set and clique. Everything we have seen, every property, every type of example. Okay, all the concepts, all the terminology, everything we have seen. Hello, Arpan?
Yes, am I audible?
Yes.
So I had a small confusion. This confusion is still there. Maximal and minimal click. I can you just tell the difference in short?
Maximal and minimal. In clique we don't define minimal, because like if I ask you minimum clique, then you will take only one vertex. Only one vertex you can take. That will be your minimum clique. What
That
difference you
is
want to know?
so sorry. Maximal and maximum. Sorry, my bad.
Maximal
Maximal
and
and
maximum.
like what can be maximal and not maximum and vice versa.
So consider this graph A, B, C, D. Okay, this graph you consider E. Now consider this graph. In this graph, look at this BDE. Look at this BDE. BDE. Is this a clique? Are they pairwise adjacent?
Yes.
Are they pairwise adjacent? So this is a clique, right?
Yes.
Yes, because they are pairwise adjacent. You can notice BDE. They are pairwise adjacent. They are adjacent to each other. So this is a clique. Is this? Can you add something more? Can you add something more? Can you add one more vertex?
No.
Can you add something more? Like for example, can I say that this is a clique? Can I say this is a clique? Is
No.
this a clique?
No.
Why no?
Because AE are not adjacent.
Very good. So this is not a clique. So can I add C? Is this a clique? Is
No,
this a clique? No. So
no,
basically, can you add something more? Can you make it bigger? Can you make it bigger clique? Can you make it bigger? No. So this is
no.
maximal. You cannot make it bigger. You cannot add something. You cannot make it bigger. So this is maximal. This is maximal. You cannot make it bigger. We cannot make it bigger. And what about this? ACBD. What about this? What about this one? This is also a clique because every two vertices, this is a complete subgraph. This is K4, complete subgraph on 4 vertices. So this is a complete subgraph. Every two vertices are adjacent. So this is a clique. Can you add something more? This is maximal. Why this is maximal? Because you cannot add something more. Tell me, in this, can you add something more? Like, can you add E? Is this clique?
No.
This is not a clique. This is not a clique because A comma E are not adjacent. So this is maximal because this is maximal. This is maximal because you cannot add something more. So this is maximal. I can say this is a clique. This is maximal also. This is maximal because we cannot make it bigger. And this is maximum also because this is the largest you can create. See, this is also clique. This is also clique. But this is the largest you can create. If you want largest, this is the largest you can create. Is the difference clear? This is maximal. This is maximum. You
So
cannot add something
ABCD over
more.
here, it is like both maximal and maximum because like both we can't add in both the perspectives.
Yes, both are maximal. Every maximum is maximal. Every maximum is already maximal. Like this is maximum. So this is maximal also because you cannot add. This is maximum. What it means? Maximum. It means you cannot add something more because that is the reason that is maximum. Yes or no?
Yes,
Is
definitely.
this clear?
Yes, sir.
So basically, it's like remember maximal maximum. For example, if you have two children, like okay, this is a child. Let's assume 4 feet, and let's assume this is the 7 feet. Amitabh Bachchan. Then you can notice this is also maximal. Height is maximal because the height cannot grow now. Like okay, after certain age, height cannot grow. So this height is also maximal. This height is also maximal. They cannot grow, but this is the maximum. So something like that.
Exactly.
So
Exactly.
maximal means you cannot make it bigger, and maximum means it is the largest. It is the largest that you can have.
Basically, maximum possible.
What?
So basically, maximum possible. Like maximum we
Yes,
can
largest possible. Yes, maximum
largest
possible.
possible.
In this graph,
Exactly.
the maximum that you can create is this. This is the largest that you can create. You cannot create larger than this. Okay.
Yes. So one
Any
more
other
small
doubt?
doubt. Yes, sir. One more small doubt I had, which is in that UGC NET question,
Hmm.
did we just use the definition and calculate the maximum possible subgraph, connected subgraph, without calculating the edges which had clicks in that?
In that question, they have given a statement. That statement is the definition of maximal clique, but they are calling it clique. That is fine. They can call it whatever they want. Okay, because once they give you the definition, you have to use that definition. Okay, so this is the idea. Now, in that question, we want to find maximal clique. In that question, maximal clique. So how many maximal cliques will be there? So very simply, you can see that this was your question. Your that question is actually like this: A, B, C, D. Okay, and there is E. So this was the question, and then you have something called like A, B, C, D, E, F, G. So this was your question. Now in this question, you can notice what we want to find. We want to find maximal. So you can notice this is maximal. This is also maximal. This is also maximal. This is also maximal. Okay. So finally, we have total 5 maximal. So we have 5 maximal cliques. This is not maximal because this you can create. See, this is not maximal because you can make it bigger. You can make it bigger like this. This is not maximal. This is not maximal because you can make it bigger. You can make it bigger like this. You can make it bigger. So this is
Yes.
not maximal. So we have 5 maximal cliques. There is only one maximum click. Only one maximum click. This is the maximum click. This is your maximum click. And you can notice that this is your maximal. And this is not a click. If I take this whole thing, this is not a click. This whole thing, this is not a click because this is not a complete subgraph. This is not a click. Is this
So
clear?
in 5 maximal clicks, like which sir, it is the minimum maximum clicks plus one more edge. So can you just repeat that?
What?
So in the 5 maximal clicks, which one are we taking? Which edges are we taking?
Edges. We don't take edges. We take vertices. We don't take edges. Click is set of vertices, subset of vertices, subset of pairwise adjacent vertices. In a click,
Yes.
we take vertices, not edges. So like this is your click. This is your maximal click. You cannot make it bigger. You cannot add something more. This ACE, this ACE, this is your click. Remember, click is subset of vertices. Click, the definition of click, understand the definition. That is set of vertices which are pairwise adjacent. This ACE, these are the vertices. So this ACE, this is a set of vertices which are pairwise adjacent. You can notice this ACE, they are adjacent to each other. So this is a click, this ACE, and this is maximal because you cannot make it bigger. If you add something more, if you add some more vertex in this ACE, if you add one more vertex, it will not become a click. If you add one more vertex, it will not become a click. So this is maximal. This is your maximal. You cannot make it bigger. But remember, for example, consider this consider this DFG. This DFG, this is also a click. This DFG, this is also a click because this is your complete subgraph, pairwise adjacent vertices. But this is not maximal because you can add B. You can make it bigger by adding B.
Exactly.
Any other doubt?
No, sir. All clear. Thank you very much, sir.
Okay. Manisha is asking, what is the modification required in the definition for a maximum click? Very simple. Just say that this would be the largest number. This would be the maximum among all. Manisha, maximum click means largest among all the clicks. Largest among all the clicks. Okay. Any other doubt, anyone? Hello, Nikhil.
Sir, am I audible?
Yes.
Good morning, sir.
Yes. Good morning.
Sir, I have a doubt in the question that tournament question that we have discussed today.
Yes. Tell me.
Sir, let's say there are 125 people.
See, if you have 125 people, then you cannot play that tournament. Like that particular
Yes, sir.
tournament, you cannot play if you have 125 people.
Yeah, sir. So I had a doubt, like according to the formula, I can simply go with the 124 games, but then I cannot.
No.
I was not
No.
able to form the full binary tree, so I got confused.
If it's not like that. See, if you have 3 people, then you cannot play that particular game.
Yes,
if you
sir.
have 3 people, then what is that particular game? See,
Chess.
the complete definition, read the complete question. In that question, the game is given to you. And what is that game? Eliminator. That is called eliminator. You know, if you watch this IPL or maybe
Yes,
some
sir. Yes, sir.
World Cup, in the cricket World Cup, there are eliminators. Once
Yes,
you
sir.
lose, you are gone. Okay, like semi-final is a eliminator, final is eliminator, quarter final is eliminator. Okay, in IPL. So anyways, something like that. So basically, once you lose, you are gone. So knockout matches, yes, Akash is saying these are called knockout matches. This is your knockout tournament. So if you have 3 people, you cannot play a knockout tournament. With 3 people, you can play something else. You can play some other tournament. You can say, for example,
Yes,
you can
sir.
play this type of tournament that A will play with B, A will play with C, B will play with C, and something like that. This type of tournament you can play, but you cannot play knockout tournament with three people.
And sir, for the case of n equal to 1000 that was mentioned in the question, sir, I got that same scenario like 125. Because for 1000, there will be 500, 500 eliminated and the 500 remaining. Then 500 eliminated, then 250 remaining, then 125 remaining. So like in
Yeah.
the
So
125, was that like in one round there will be 125 members remaining. So like how are we going to like create those matches then?
Yeah, your point is actually nice. So actually that question I took from Kenneth Rosen directly. From Kenneth
Okay.
Rosen I took it. Maybe they did not think like that. I agree what you are saying. I agree with that. Because see, for example, what you are saying is something like if you have 10 people, then we, for example, if you have 6 people, like
Yes,
if you
sir.
have 6 people, if you have 6 people, we cannot play, right? Like if you have 6 people, then we cannot play.
So it
We
has to be
cannot
a
play.
power of 2 power n.
It should be a power of 2. I agree. Okay, so
Yes, sir.
yeah, I agree with what you are saying. I agree. So actually that question I have taken from Kenneth Rosen. Maybe they have given some other data, like, but I just copy pasted, like, okay, so maybe they did not, there must be a typo. You can make it 1024.
Yeah, then it would be
Just
fine.
make
Like,
it 102.
yes, sir.
Let me make 1024. Okay.
Yes, sir.
Yeah, that is very nice observation. What is your name? Nikhil.
Yes,
Yes,
sir.
very nice observation. So because you must have, definitely you must have power of 2. You must have power of 2, like 2 power k people. You must have 2 power k people, because else we cannot play this tournament. That's the simple point, right?
Yes, sir.
This tournament, this particular tournament, we cannot play if you have 1,000 people. This type of tournament we cannot play. So
Yes, sir.
1024 you can have, and then finally the answer will be
1023.
1023. 1023. Okay, so you can change this basically. Okay, very simple. Yeah, that is a nice observation.
Got it, sir. Thank you.
Yuvraj is saying with 3 also it's fine. Play some 2, find one winner, and play with him the remaining.
That would be unfair type of scenario.
Yeah, that would be unfair, but ultimately we will get a full binary tree.
Sir,
See, we will get a full binary tree. If we do like that also, the answer will not change. So maybe that is the reason.
sir, full binary tree, how
We see what
last
Yuvraj is saying. Yuvraj is saying that, for example, if you have 3 people, then Yuvraj is saying that play these 2, and then you play these 2. This is
so
what
but it
Yuvraj is
would
saying.
be a like binary tree, but not a full binary tree.
It will be a full binary tree, right? It
Uh,
will be a full binary tree.
the full
So,
binary tree has to be like all levels filled, right?
no. Full binary tree does not say that. Full binary tree does not say that. Full binary
Okay.
tree means you have like this. This is also full binary tree. A, B, C, D, E, F, G. This is also full binary tree.
Okay, so every node has to be 2 children.
Yes, every node has either 2 or 0 child. So that is
Okay.
also a full binary tree. So actually in this question, if you don't have, okay, maybe actually see, if this question comes in the exam, if this question comes, then definitely they should give some more information, because you can
Yes,
notice,
sir.
if you play 2 power k people, there is no problem. If you play 2 power k people, okay, then there is no problem. But if you
Yes,
have
sir.
n people, like some maybe odd, any number if you have, then you can have this type of tournament. This
Yes,
type
sir.
of tournament you can have. So ultimately the answer will be same, whether you have like, but the question will change. Okay, you have to
Okay.
modify the question. In the GATE exam, if this question comes, then maybe they will mention like this type of thing can happen. If you don't have
Okay.
partner, then you will automatically go to the next level. Okay, so something
Yes,
like
sir.
that.
Yes, sir. I got it.
Okay, so anyway, you can like, if yeah. So this is called tournament problem, as I told you. So in this tournament problem, first the definition must be given. Like, okay, this is a standard problem, but they will give you the definition. And once they give you the definition, which type of game they are playing, depending on that, you can solve. Okay.
Okay, sir. Okay.
Any other doubt?
No, sir. Got it. Thank you.
Yeah. Anyone has any other doubt? Which question? Can you tell me? Manisha, which question? Okay, so you are asking this one. See, let us assume that, see, let us assume. So this is basically, okay, I am again telling you the proof. I'm again telling you the proof. Let us assume you have a graph G. This is your graph G. In this graph G, let us assume you have maximum independent set. You have maximum independent set. Maximum means this is the largest. You cannot create larger than this. Agree, Manisha? So in this G, you have maximum independent set S. This is your maximum. This is the largest. You cannot create larger than this. You agree? So there is no larger. So this is what you have to agree. That okay, there is no larger independent set. There is no larger independent set than S in G. That is the definition. That is the definition of maximum independent set. Now, tell me what will happen in G complement. In G complement, what will be this S? This S will definitely be a clique. This is fine. Is this clear? Because here in this graph G, S is independent set. Means in this S, you have pairwise non-adjacent. You have pairwise non-adjacent in this S. In this S, they are pairwise enemies. I can say they are pairwise enemies. Everyone is enemy of each other. So in the G complement, they will become pairwise friends. There will become pairwise adjacent. So in G complement, this S will be a clique. You know. Now, can you have bigger clique? Now, can we have bigger clique? Can we have bigger clique than this S? So this S is a clique, but can we have bigger clique? Bigger clique M than S? Can we have bigger clique M than S in G complement? In G complement, can we have? So let us assume you have. This is my question. See, S is a clique, that is fine. But now let's see, can we have a bigger clique M than S? Bigger than S, can we have in G complement? So assume you have. Assume M, which is greater than S. Okay, means M is bigger. Assume M, okay, which is greater than S, is a clique. Is clique in G complement. Then what will be this M in G? Can you tell me? See, this M is a bigger clique. I am assuming that this M is the bigger clique. Means in this G dash, there is a bigger clique. This S is a clique, but there is a bigger clique M. Now tell me what will happen in G. In G, what will happen? In G, this M will be what? This M is a bigger clique. This M is greater than S, and this M is a clique. So in G, what will be M? In G complement, M is a clique. Then in G, what will be M? M is independent set. M is independent set. Yes, correct. Because in G complement, M is a clique. M is a clique. Means pairwise adjacent. So in G, it will become independent set. So now you can notice there is a contradiction. In G, M is independent set. You are saying that M is independent set. And you also know that M is greater than S. M is independent set. M is independent set. And you are saying M is greater than S. It means what? S is not maximum independent set. It means what? It means S is not maximum independent set. And this is the contradiction. Is this clear now? Let me know. Manisha? Simple argument, like forward backward argument. So simple. This is called forward backward. Like I can say loop argument. This is a loop argument. Okay, like you go from here to there, and then you go from there to here. Okay, so like that. Any other doubt? Okay, thank you everyone. See you tomorrow. So today we have, in the evening, we have digital logic class. Okay, today digital logic will start. The first class was only, I can say, it was just a warm up. It was just a starter. Okay, so today digital logic will start. Okay, thank you everyone. From 8 p.m.